Chatelier was a French chemist who decided he wanted to study systems at equilibrium. Sounds kind of boring to me, especially since we know that systems at equilibrium, macroscopically, what we can see with our naked eye, look like nothing's going on. So in my mind, studying systems at equilibrium would be a lot like sitting and watching a wall. Okay, nothing's happening. And Le Chatelier realized this as well. He said, hey, this is actually boring, studying systems at equilibrium. I want to shake it up a bit. And so he did. Not like actually physically grabbing the chemicals and shaking them, although maybe he did that too, I don't know. But he said, you know what I'm going to do? Instead of sitting here watching these systems at equilibrium go about their day, everything's fine and great, I'm going to implement some changes. And I'm going to see what happens when I change some things about this system at equilibrium. He said, I'm going to stress this system out. That's what he called the changes that he made. He called them stresses. And what he noticed is that when he stressed out these systems at equilibrium, they all responded to make adjustments to kind of reestablish equilibrium. Equilibrium's like a happy state, okay, that these chemical systems want to be in. And when they get stressed and taken away from that happy state, they want to make an adjustment to get them back to their happiness. Okay, those adjustments are called shifts. Think of it this way. Make it personal. Your life is great. You're going along your day-to-day routine. Everything is business as usual. You're happy. Okay? All of a sudden, your chemistry teacher drops a bomb on you in class. You have a unit test in a few days. Oh my goodness, what a stress. Now, humans respond to stress in multiple different ways, right? Some people will respond to stress like they can't eat because their stomach clenches up and gets all nervous. Some people can't stop eating because that's how they're dealing with the stress. Some people need to exercise to work with their stress and bring it back down to a manageable level. Some people find that they are just needing to sleep and sleep and sleep. People respond to stresses, even the same stress in different people, will get different responses. What's nice about chemical systems is that they're not made of people, okay? And these chemical systems, what Le Chatelier found was that when he implemented a stress, regardless of what system he implemented it on, all systems responded the same way. Okay, so humans have different responses for stress. Chemical systems, not so much. They all respond to stress in the same way. And the way that they respond to stress is called a shift. Okay, so when we talk Le Chatelier, we're talking about stresses or changes, and we're talking about shifts or adjustments that the system makes to get itself back to equilibrium. Okay, Le Chatelier took a look at three, I guess let's call them categories of changes. He took a look at what happens to equilibrium systems when he changes concentration of reactants or products, what happens when he changes the temperature of the system, and then what happens when he changes the volume or the pressure of the system. We're going to go through all three of these with some visual examples so you can see exactly how these shifts work to respond to the stress. First up, changes to concentration. How do we change the concentration of substances in a chemical system? Well, we either add some of the substances in the chemical system or we remove them. And when we're talking about a chemical system, remembering that that's reactants and products. So when we want to change concentrations in a chemical system, we can either add or remove either a reactant or a product. Wild. Here's the pattern that Le Chatelier noticed. I would highlight that. He's noticed that these equilibrium systems would shift away from additions and towards removals. What does that mean? When I'm adding something to the system that increases the concentration of either a reactant or product, the system shifts away, okay, from whatever was added. So if I added a reactant, the system would shift away from that reactant side towards the product side, okay? If I removed something from the system, I removed a chemical from the system would shift towards what was removed. So if I were to remove a reactant, the system would shift towards the reactant side, okay? Really important to note that Le Chatelier, when we talk about him, we talk about his ideas and his studies being a principle, okay? So in being a principle, we're only using his ideas to help us make predictions of what's going to happen without so much of an explanation as to why. Okay. For our example, for concentration changes, we're going to use this equilibrium system, which is called the iron thiocyanate equilibrium. And we're going to take a look. We're going to make 3 different stresses to this system, changing concentration of reactants or products or both. We'll see. Okay, let's take a look at what that would look like. So for our first equilibrium system that we'll take a look at, let's look at this iron thiocyanate equilibrium system. What we have done is we've mixed iron 3 ions, thiocyanate ions, and that's formed an equilibrium system making iron thiocyanate. It's a lot of syllables to go through to talk about this equilibrium system, but we're just going to work with it, okay? Now, I've set up 4 different test tubes with this equilibrium system already in it, okay? So what we can see is when we've got iron 3 ions, which are yellow in color, and we mix those with something colorless, and then iron thiocyanate ions, which are red in color, yellow plus colorless plus red is going to make this orange color that we have here. Okay, so all 4 of these test tubes contain the same thing. It's the iron thiocyanate equilibrium system. As you can tell, just looking at them, we could sit here and watch that. It'd be pretty boring. So let's stress these systems out. Let's impart some sort of change that is going to upset the system and cause it to need to shift to re-establish equilibrium. So remember, once a system's at equilibrium, it wants to stay at equilibrium. When we stress it out, it's going to shift, the system will shift so that it gets back to equilibrium. Okay, I'm going to leave this first test tube here as is. That'll always be the one that we refer back to. So we can see, okay, well, what was the initial color? Okay, the first stress I'm going to do is I'm going to add some, can you see that? Iron 3 nitrate solution. Okay, so here's what I'm doing. I'm adding iron 3 nitrate solution. Okay, when I do that, when we're talking about what is the stress, we have to talk about how does adding this impact this system? Be specific. Okay, so this is what we're doing. How does it stress the system? Well, it stresses the system, if you remember, okay, when we add these aqueous solutions. Remember, an aqueous solution of an ionic compound is going to have dissociated. So when I add, oops, didn't really save room for that coefficient. When I add iron 3 nitrate solution, what I'm doing is I'm adding iron 3 ions and nitrate ions. So what is the actual stress to the system here? Okay, the actual stress to the system is I'm increasing the amount of iron 3. How do I know that that's a stress to the system, not the nitrate? Well, because nitrate is not in the system, first of all. Secondly, nitrate is most often a spectator ion. So the stress, the actual impact that I'm having on this system is that I am increasing the iron 3 concentration. Okay, I'm increasing the iron 3 concentration. So I'm adding more of this yellow colored ion. I'm going to add it to the second tube here. And you can see, like, even in the dropper, it is yellow. So when I add something yellow to a system that is like a super pale orange, what do we think should happen? I'm only going to add a couple of drops. Oh, weird. Okay, that is bizarre. Maybe you thought that adding something yellow to a system that was orange would make it lighter. And I mean, if we were in kindergarten mixing finger paints, yes, that's exactly what would happen. Okay, unfortunately, we're not in kindergarten. Remember those good old days? Wish we could go back. We've added yellow and this system has gone darker. It's become more red, you could say. Okay, so what happened? Remembering Le Chatelier's principle tells us that systems will shift away from what is added. So we've added iron 3, which is on the reactant side here. The system is going to shift away from the side that has the iron 3. So it shifts away from the reactant side, meaning it makes more products. That's what a shift is all about. What is eventually going to be made more of. So it makes more, even though we added yellow, the system made more of this iron thiocyanate, which is red. Okay. And to make more of the iron thiocyanate, which is red, it has to use up iron 3 and thiocyanate. So we actually, in adding yellow, get at the end result, and by end, that's in air quotes, okay? End means equilibrium. The equilibrium result is that we actually use up more yellow, more colorless, and make more red, which is why this system goes darker. Okay, what is the shift? So the shift is towards, you could say the product side. What we see most often is a direction. That's actually why I wrote left and right letters up there, because sometimes I have a hard time remembering what's left and what's right. If you do too, do that on all your equations. That's my tip for you, for those of us who have a hard time with directions. Okay, the system shifts to the right. Okay, and what was the observation that we saw? Well, we saw that the system got darker red, or you could say darker orange, whatever this color looks like to you. Okay, we all see colors differently. Well, isn't that interesting? Let's take a look then at what happens when I stress this system out in a different way. So to my test tube 3, what I'm going to do is, where's my next solution? I have some potassium thiocyanate. So that's what I'm going to do next. I'm going to add some of this guy, potassium thiocyanate solution. Okay, this is also an ionic compound in solution. So remembering that means it's going to dissociate into potassium ions and thiocyanate ions. So what is the specific stress to this system when we take a look at it? Well, the specific stress, the potassium is not going to have anything to do with it. I'll just move this guy out of the way for a quick sec. Potassium is not going to have anything to do with it. There's no potassium in here, and plus potassium is most often a spectator ion. Okay? So then what does that leave us? Well, this SCN, oh, hey, look, there it is in the system. Okay, so the stress that we're going to do is we are going to increase the thiocyanate concentration. Before I do that, pause me. Okay, make a prediction. What are we going to see? That's where the prediction is, the observation. What are we going to see? What do you think the color is going to be? Remember, thiocyanate is colorless. Okay, let's add some of this. Let's get some potassium thiocyanate in there so you can see there's colorless. I'm going to add it to test tube 3 here. Okay, not as dramatic. Isn't that interesting? I'm surprised by that. Okay, but I think if we're comparing to like test tube 1 or even the one right next door, test tube 4, okay, we can see that this system did get a little bit darker. I'm going to add just a little more. Let's see what happens. I don't think it's going to get much darker than that. Okay. However, it did get slightly darker, right? I think we can agree when we take a look at this. I'll go from the top so my hand's not altering the color. Test tube 4 is slightly lighter than test tube 3. Okay, so what happened? Well, the system, we can't even say it got red. It got darker, and you could put slightly darker if you wanted. I'm not here to judge. Oops, that's like right in the way. Oh my goodness, now I'm in the way. Okay, here we go. It got darker. So what does that mean? How did this system shift? How do we make that make sense? Well, to get darker, it's certainly, we weren't making more of this yellow and colorless. That's going to lighten the system. Okay, so instead we must have created more of this iron thiocyanate ion, okay, which is the darker red in color. Therefore, we must have shifted to the right. Okay, why did that happen? Why did that happen? We increased the concentration of thiocyanate. The system wants to shift away from what's added, okay, because we want to use up this extra thiocyanate. So the system shifts away from what's added, using up the extra thiocyanate, using up a bit of iron 3 ions in this equilibrium to make more of this guy. Okay, more of the iron thiocyanate. Okay, so that is a shift to the right, or you could also say a shift to the product side. All right, last one. I'm going to add see that? Oh, no. Which way do we go? There we go. I'm going to add some sodium hydroxide. Think about this for a minute while I erase. All right, I'm adding sodium hydroxide. And then again, if we look at what's actually present in this solution of sodium hydroxide is sodium ions and hydroxide ions. Okay, whoops. Ta-da. Okay, so what's the stress on this system going to be? Sodium ions. Okay, they're not in this equilibrium system. Go on to the next. Hydroxide ions. Hey, wait. They're not in this equilibrium system either. Interesting. What do you think we are going to see? I'm going to add it to test tube 4. And actually, you know what? I'm moving test tube 1 down so we can have a little side-by-side comparison there. I'm adding this sodium hydroxide. What do you think we're going to see? It's weird. This was a weird one because we don't have sodium, we don't have hydroxide anywhere in this particular equilibrium system. So probably nothing should happen. Do you think that? Let's see. Anything? I'm going to shake it. Oh, yeah. I got a little bit, but it might be hard for you guys to see, so you might just have to trust me. I'm going to add a little bit more. Oh, that didn't even have anything in the dropper. Okay. Okay, I don't know how clear this is going to be. Let me just shake this guy a little bit. Get him agitated. That's what I like to do. Okay, let's do a side by side first. Okay. I think if we go side by side, oh, it's just not showing up super well. I can see it a lot better. But this guy is actually a little bit lighter than our control number 1. Also, I'm going to bring this close and I'm going to put some paper behind it. So I wonder if you guys can see. Whoa. Can you see that that's cloudy? We've got a little cloudiness, a little chunkiness. Here, I'll shake her up again. And then the chunks can start floating around. Is that clear? Do you think I'm making this up? I'm really not. Okay, there are little chunkaroos in there. Now, with these chunks, what is going on? Okay, okay, I'll give it to you. It's not the most beautiful example. Okay, as in it's not the easiest to see. So trust me on this. The color did get lighter. There were little chunks in there. There weren't chunks before. So what's happening? Well, let's, instead of going, okay, what's the stress, what's the shift, what's the observation, let's work backwards. What did we see? Well, we saw the observation was that the system got ever so slightly lighter. But we'll call it lighter. It's good enough for our purposes. You know, it's got me wondering. I've got this big bottle of the thiocyanate mixture here. I wonder if I could no, let's not do that. Let's not push our luck. We don't need to use a whole bottle. I was just thinking maybe if we had like a lot, makes the color more intense, and then if I dumped in a lot of sodium hydroxide, it could make that color change more obvious, but that's okay. We'll leave it. You'll take my word for it. You'll trust me. Okay, I wouldn't lie to you. Okay, it got lighter. How did the system get lighter? What's the only way the system could get lighter? Well, it could only get lighter if it shifted back towards the reactant side or to the left side. Okay, we saw shifts that took us to the product side and how that got darker. So we must be, if we're looking at lighter colors, shifting more to the left. How on earth did that happen? How did we shift to the left? Okay, in order to shift to the left, by changing concentrations here, guys, there's only 2 things we could have done. One, we could have increased the concentration of products. If we increase the concentration of products, the system shifts away from the products. So it would shift back towards the reactant side. That would be one way to get this system to shift left. A second way would be if we decrease the concentration of either of these 2 reactants. Systems shift towards what's removed. Okay, so if we decrease the concentration of these 2 reactants, the system would shift back to the left as well. So what did we do? Well, we know we didn't increase the concentration of thiocyanate. We don't have this iron thiocyanate down here. So we must have decreased the concentration of something over here, but how? Okay, well, here's the how. I'm going to move this because I might need a bit more of the board for your explanation. Okay, so, but how? Well, here's what happens. You guys see this hydroxide ion floating around, okay, in solution? Well, what's actually going to happen is when I add sodium hydroxide to this system, the hydroxide ions that are floating around are going to start eyeing up those iron 3 ions that are floating around. And they're going to say, hey, let's get together over here somewhere, okay? And what they're going to make when they get together is this iron 3 hydroxide, but check out the state on this guy. It's a solid, okay? So they're going to make iron 3 hydroxide, which is a solid. Solid means precipitate, hence the chunks that were floating around there, okay? Ever so hard to see. And when we precipitate something out of solution, we decrease its concentration. So removing iron 3 from solution decreases its concentration. When we decrease the concentration on the reactant side, the system will shift back towards the reactant side to make more. So what's the stress? What stress did we do for this system? We decreased the iron 3 concentration. Okay, wild times. Now, anytime you're adding something to a system that isn't a part of the system, this is my hot tip for you, okay? You have to get those alarm bells in your little heads going off. And you have to say, ooh, this will likely precipitate something out of the system. Okay, in the other two examples, when we added the iron 3 nitrate, the potassium thiocyanate, there was always something in those compounds that was in the system. Here, in this case, with adding the sodium hydroxide, there is not. Alarm bells, precipitation. What's precipitating? We know that anions aren't going to get with anions. Cations are going to be the ones that get with the cation. Or sorry, with not the cation, with the anion. Okay, to precipitate out. There's our first equation. Okay, so we've seen visually, looking at the chemical system, what happens when we change the concentration of reactants products. Let's take a look at what does that look like graphically. Here I've got set up a graph for us to look at. This graph is going to have our concentration of reactants and products on the y-axis. Okay, and please note that this is what we would call a qualitative graph, not a quantitative one. So there's no numbers on mine. Anyways, you might sometimes see one with numbers, but what we're going to draw is just going to be qualitative. Okay, no numbers. The relative amount of concentrations, I'm just going to be drawing lines. So don't get hung up on that piece. Okay. What happens along the x-axis is we're taking a look at time, passage of time. Okay? And then we've got these 3 vertical lines, and they correspond with the 3 stresses that we made to this system, okay, at different times, A, B, and C. So what are we going to do? Well, first of all, we're going to start by assuming that this system was at equilibrium when it started, which it was, okay? The equilibrium had already been established. So, taking a look here, okay, what we can do is we can start by showing an established equilibrium, which again, all lines will be horizontal and parallel to the the x-axis. That was hard to say. First of all, I'm going to draw my iron 3 ion right there. Okay, horizontal at equilibrium. Next up, I'm going to draw my thiocyanate ion. And again, these, where I'm drawing them on the graph, it doesn't mean I have more than one than the other. Okay, I'm just drawing my lines. Don't get hung up on that. I'm using different colors so that I can see a little bit better on this graph so that things don't get kind of mixed up. You can use different colors as well if you'd like. And then lastly, our product here, that iron thiocyanate ion. Also horizontal, okay? Everything's at equilibrium. So what happened at time A? Well, at time A, I added some more iron 3 nitrate, and that was dumped in all at once, okay? So the concentration, the stress to the system was a big increase in the concentration of the iron 3 ion. So it jumped up right away. But even though the iron 3 ion is yellow in color, adding it to this equilibrium system made the system red. In fact, the system shifted away from what was added to make more products. How does that shift work? Well, that shift works by using up, slowly decreasing the amount of iron 3 that we have present. So we've got two things happening in this graph that I want to point out to you. First of all, we have this big spike. Okay? The spike represents the stress. Okay? The spike represents the stress that when it was made directly impacting concentration of something in the system, in this case, iron 3. Then we have the bump. Okay? The bump shows the shift. The bump shows the shift. In the shift, concentration decreases over a period of time. It doesn't decrease all at once, okay, the same way that the concentration increased all at once when I dumped a bunch more in. So that's how it's showing the shift, because it happens a little bit more gradually. Okay. Let's talk about SCN, the thiocyanate ion. Now, it was also a reactant. We did not have any direct impact at time A on its concentration. So there's no spikes here. Okay. However, by virtue of it also being a reactant, and because the system shifted away from the reactant side, so the system shifted to the right, that means the SCN as a reactant also got used up and will also have a little bump down in its concentration. Okay, also have a little bump down in its concentration. Then, look at our product. We shifted away from the reactants, meaning towards the products, the right side of the equation there. In doing that, we actually made more product. And we saw that that's what was responsible. Oops, wrong color. Oh my goodness. That's what was responsible for the red color that we saw happen in the system. Okay, so we must have made more iron thiocyanate in that shift. Okay, so the system reestablishes equilibrium. It floats merrily along until time B. Dun, dun, dun. What happens there? Well, we added that potassium thiocyanate, and in doing that, had a direct impact on the concentration of thiocyanate. Big spike up for that. We dumped a bunch in all at once. And again, because we added that thiocyanate, the system shifts away from additions. So it shifts away from the reactant side because thiocyanate is a reactant. And what we see is a little bump down so that the system can reestablish equilibrium. Same idea with the iron 3. Because it's a reactant, it also gets used up. So we see a bump down. Okay, and again, because the system shifted to the right, it ended up making more iron thiocyanate. So we get a bump up. Okay. Last stress. Same idea. We added that sodium hydroxide. And what did we see? We saw that this system went colorless. Why did it go colorless or lighter red? Okay. Why did that happen? Sorry, did I say lighter red? Like towards the yellow side. Why did that happen? Okay. Well, what we did in adding that sodium hydroxide was we removed the iron 3 ion. So the iron 3 ion hanging out in the chemical system met up with that hydroxide ion that we added into the system. And if you check a solubility table, iron 3 hydroxide, not super soluble. Okay, so what actually happened was a precipitate formed. And in the formation of that precipitate, that's how we removed iron 3 from the system. Okay, so we removed it. So we had a big spike down because we removed it all at once. Okay. The system then says, I have to shift to kind of rectify this stress here, to fix it. And it shifted back towards the reactants, towards what was removed, to the left side of the equation. So we actually ended up being able to remake some more iron 3, which has that yellow color. In addition, we made some more thiocyanate, okay, which is colorless. And we took away, or we used up our iron thiocyanate. So we took away or used up that red color, leaving us with predominantly more iron 3, yellow ions, and thiocyanate, colorless ions. So that helps to explain our color change there. So we've gone through concentration changes. It's really important we understand kind of what was going on with changes to concentration, because changes in temperature we're going to be taking a look at with a similar lens. When we make changes in temperature, oops, typo, oh my goodness, can you imagine such a thing? Just kidding. Changes in temperature are made by either heating or cooling a system. So when we take a look at this system, we want to think of energy to be like it's just another substance in the chemical reaction. And you can see in the equilibrium system that we're going to look at, I've written our energy term as though it is part of the system. Now, energy doesn't really have like a concentration, but sometimes, like when we're looking at Le Chatelier's principle, it helps to think of it that way. Why does it help to think of it that way? Because when we take a look here at the shifts that these systems are going to make for temperature changes, they're actually the same as, the shifts are the same as they were for concentration. What happened in concentration again? Oh yeah, the system shifted away from what was added and towards what was removed. So here we have energy in this particular system we're going to look at. Here we have energy as a reactant. I want you to think about, if we are heating this system, which way would the system shift and why? Okay, if we are cooling the system, what does that do to the energy of the system? Which way will the system shift? Let's take a look at what that looks like. Okay, next equilibrium system that we want to take a look at is this one right here. Oh, and right here. Okay, so we're taking a look at a gaseous system. So everything in it is a gas. And in fact, it is, so all equilibrium systems have to be closed. This is our closed system here. It's a sealed glass tube that contains some N2O4 and some NO2 gas. Okay, this N2O4 gas is colorless. NO2 is a dark brown. When you mix the two of them, you get a light brown. I know this probably looks a little orange. Calm down. Okay. What's important to know? We're going to be taking a look at temperature changes. Okay, and how does changing the temperature affect your equilibrium system? So we're going to heat the system, we're going to cool the system. That's the nice thing about temperature changes, is there's only two things we could do. When we're talking about temperature changes, we're going to consider energy as just another substance in the chemical reaction. So I've written it there, it goes on the reactant side or the left-hand side. Okay, and then we treat these changes the same way as we would if this was an actual chemical and we were changing its concentration. Energy doesn't have a concentration, okay? But it helps us to think about, okay, if I'm increasing the concentration of energy, aka heating the system shifts away from additions. Or if I'm decreasing the concentration, air quotes, of energy, then I'm cooling the system, I'm removing energy, the system shifts towards what has been removed. Okay, so that's exactly what I'm going to do, because in fact I have not just one but two of these glass tubes, and I'm going to stick one in hot water and I'm going to stick one in cold water. Let's talk about the stresses before I get these up there, because I think it's going to take away my view of the whiteboard. Knowing that, okay, heating the system, cooling the system, that's what I'm doing. What is the specific stress on the system? Well, when I heat the system, I am increasing the energy. And when I cool the system, I am decreasing the energy. Okay, I want you to think, as I'm just getting my beakers of water set up, I want you to think about what are the shifts we're going to see for these. What are the shifts we are going to see? Ooh, that's hot. Okay. Well, I know you can see that this is cold water because you can see the ice cubes. This is hot. If you look really closely, you can kind of, it's really hot, I don't want to touch it. You can kind of, okay, for you, I'll sacrifice my fingertips. You can kind of see the condensation, there you go, on the glass. So this is hot water in that beaker. All right, here we go. If only I had a third, and then we would have something to like compare back to, but alas. Okay, cold water, hot water. Ooh, yeah. I want to move this. I wonder if you guys can see. Check out this hot tube. I don't know if you can see it. No, I think I missed the mark. Anywho, oh, kind of. Okay, if you look down right by the top of the glass, it kind of looks a little like, yeah, looks a little wizardy, like there's like this weird colored gas being formed, which there is. Spoiler alert, there is. Oh, hey, back over here with our cold glass, that has gone significantly lighter. And in fact, when we compare hot and cold, you can see there is a definite difference between the two colors, between the two tubes. Okay, very interesting. Now, what do we want to do? Well, I don't think we need to sit here and look at these necessarily for too much longer. You've seen your color change. So now let's talk about what's happened. I'm going to just move that over there. That over there. Let's talk about what happened. Okay, where was the shift? So when we increase the temperature of the system, okay, it was adding energy, and we know that the system shifts away from what's added. Okay, so shifting away from what's added, energy is on the left-hand side, that means the system will shift right. And what did we see? What did we see with our hot tube? Well, we saw that it got darker. We'll say darker brown. There we go. Okay. What about our cold tube? So cooling the system removes energy. Got it. Okay, the system will shift towards what's removed. Okay, so the system is going to shift back towards the left. And what did we see with that? Well, what we saw was all right, brown. Our tube was definitely a lighter brown color. There we go. Temperature changes. Le Chatelier, bless it. So back here to look at graphically, what did we take a look at here? Same kind of setup for the graph. Just filling in all the blanks here. And then let's take a look at what happened, okay, for this particular system. So we only had two different substances here, and we were at equilibrium from time 0. So I'm just going to draw my lines in. Here's my N2O4, And here's my NO2. So at time 8, I heated the reaction vessel, and we saw that heating the reaction vessel created definitely a darker brown color, which shows that we're making more NO2. Okay, so again, why did that happen? The system shifted away from what was added. What did we add? We added energy. Okay, so the system shifted to the right, to the product side, to make more of this brown NO2 gas. Again, it was the shift that made the NO2 gas, not the stress. Okay, the stress was increasing the temperature. The shift was let's shift to the product side or to the right-hand side. In doing so, we decreased the amount of N2O4. Okay, so just little bumps here for both of them. All right, so we say our equilibrium gets reestablished, then we cooled the reaction vessel. What stress did this place on the system? Well, it removed the energy or decreased the amount of energy, okay? So the system therefore shifted, and we saw that lighter color. The system shifted back towards the reactant side or to the left of this system, making more N2O4. How did it make more N2O4? Just a little bump. Okay? Then, in making more N2O4, that means we had to use up our NO2, so that's going to have a little bump down. Graphically, here's what temperature changes look like. Okay, the last set of changes that we're going to take a look at are stresses for pressure and volume. Okay, how do we change pressure and volume? Well, first of all, we have to know that we're talking about gaseous systems only. Okay. So we need to have gases present in order for changes to pressure and volume to have some kind of an effect. Okay. So how do we change the pressure? We adjust the volume of the reaction vessel. Okay. Well, how does that work? Think back to previous studies of chemistry and remember that we have an inverse relationship between pressure and volume. What does that mean? It means when we increase the pressure, we decrease the volume. And when we decrease the pressure, we increase the volume. Okay. The next 2 points I have written on there talk about how the gaseous system will shift in response to that stress of a pressure/volume change. Okay. I want to make an analogy for you guys. Let's think about this, okay? Let's think about, it's Friday night. You're going to have some friends over, okay? But you're a teenager and live with your family, okay? So think about who's home at your house on a standard Friday night. Yeah, probably everyone. Parents, siblings, I don't know who else lives with you, pets. So if you're going to have friends over, where are you going to hang out? Most teenagers will say, if I have friends over, we just hang out in my room. Okay, why? Because teenagers don't want to associate with the rest of their family. They're embarrassing. I know, I've got you. Okay, so you and your friends are going to hang out in your bedroom. Now, if your bedroom looks anything like my bedroom did when I was a teenager, it is small. So how many friends am I going to have over if I'm only hanging out in my room with them? A couple? Yeah, like I would say 2 friends max. So provided that you have 2 friends in total, the 3 of you could hang out in your room. How does that work? Well, family's home, so there's your pressure, right? Family's home, pressure is increased, which means you have only a smaller space or a smaller volume, if you will, of your house to hang out in. So therefore, you are going to have only a few friends over for what I like to call your bedroom party. Okay, bedroom party. Only a couple friends. Now, say it's a different Friday night. Ooh, parents are out of town. You got younger siblings, they're staying at your grandparents' house. You've got the house to yourself. No pressure here. What are you going to do? Probably have hundreds of people over. Just kidding. Disclaimer. Do not have a house party when your parents go out of town. I did that once, like over 20 years ago, and I still have not lived it down. So learn from my mistakes. Don't have a house party. But say your friends are responsible and kind, unlike mine at the time, okay, you would have the whole house to hang out in. How many friends can you have over if you have the whole house and you're not just like confined to your bedroom? Yeah, you can definitely have way more friends, okay, provided, again, that you have more friends. Not all of us do. So, when we have decreased pressure, aka parents, other family members aren't home, we have access to the whole house, aka an increased volume. So we can have more friends over. I call that a house party. Again, with the disclaimer, don't have a house party. That's the last time I'll say it. Okay? What's the difference? Increased pressure, decreased volume, fewer moles of gas. So the system shifts to the side with fewer moles of gas. That's this one here. And then when we can have a house party that we're definitely not going to have, we've got that increased volume. The system shifts to the side with more moles of gas. Okay, shifts to the side with more moles of gas because you can have more friends over. Okay, that's the analogy I want to make on our pressure and volume changes. Now, I don't have compressible compartments to look at housing this nitrogen dioxide, dinitrogen tetraoxide system. So you have to close your eyes and picture it. Take my word for it. Or you can go search up some other YouTube videos that will have this demonstration. Okay? So it's important to note that when we take a look at total number of moles of gas, we're considering every mole of gas or every molecule of gas to be the same size. So we're only counting coefficients. So in this particular system, we have 1 mole of dinitrogen tetraoxide, okay, or aka 1 mole of gas altogether, and we have 2 moles of nitrogen dioxide, 2 moles of gas altogether. Hoping that you recognize 2 is more than 1, okay? So think about how is that going to impact our system. When we increase the pressure, okay? When we increase the pressure, so we're taking a look here, and decrease the volume, the system will shift to the side with fewer moles of gas, aka the dinitrogen tetraoxide. What would you see? You would see a lighter color. Why? Because we are making more of the colorless gas. When we increase the pressure, decrease the pressure and increase the volume, the system will shift to the side with more moles of gas, meaning the nitrogen dioxide. Okay, what will we see? We will see a darker brown color. Why? Because we're making more of the brown gas. Okay, what does this look like graphically? Let's find out. Prepare to have your mind a little bit blown. All right. So, again, setting up my graph. Concentration, time, And then we have our happy little system at equilibrium to start. Here we go. NO2. And then we're making, again, those two changes, two stresses here for this guy. All right, first thing we did at time A was we increased the pressure. Increasing the pressure decreases the volume, okay, which means that's a bedroom party, all right? So what are we going to see? We're going to see the system shift towards the dinitrogen tetroxide. I'm just going to write this down. I know I didn't write it on our other graphs, but I'm just going to keep track here. So system A was increased pressure, which means we decreased the volume. Okay, increased pressure, which means we decrease the volume. Now, what does this look like graphically? Whoa, well, I'm going to show you. You're going to be confused, but then we're going to talk about it, okay? Whoa, what? Okay. So remember that spikes show the stress. Spikes show the stress. What the heck happened here? Both my N2O4 and my NO2 spiked up. Why? Well, we have to remember there's also a relationship between volume and concentration. And that relationship is also inverse, right? If we take a look at even our concentration formula, C equals N over V, because the volume is in the denominator, when volume decreases, concentration increases. And because we are making that change to the whole reaction vessel, where both the N2O4 and the NO2 are residing, we'll say, it's going to impact the concentration of both substances, and it's going to increase the concentration of both substances. Again, that is just because we've changed the volume of the container. So both substances have a big spike in their concentration, and then the shift happens, okay? So here is our spike to show that this was the stress, okay? And then that's followed by the shift, represented by a bump. We shift to make more N2O4. That's why this continues to go up, the N2O4 line. And in doing so, we are using up the NO2, which is why that concentration decreases. Equilibrium gets reestablished. Then what happens at time B? Well, at time B, we're decreasing the pressure, parents out of town, which means we're increasing the volume, house party, okay? Which means the system will shift to the side that has more moles of gas. That's our NO2. So what happens? All right, let's talk. Concentration does a little something like that for the NO2, okay? For the N2O4, it's going to do that. So again, what's going on here? Well, taking a look at our relationship between now volume and concentration as being inverse, the volume went up, therefore the concentration of both gases decreased. That was our stress. That's why it's represented as a spike. Then the system shifted to make more NO2. Okay, so shifted to the right, to the product side. So the concentration of NO2 bumps back up, whereas the concentration of the N2O4 bumps down because it's getting further used up. That is pressure and volume changes. Okay, so think about your house party versus your bedroom party, how many friends are you having over? The number of friends you're having over is the same idea as the number of moles of gas. I want to talk about one last change that we didn't do, but it happens at this fictitious time C. Okay, and I'm going to show you. Notice how my lines stay the same. At time C, I'm going to say, I'll write it down here, I added a catalyst to the system. So we can see graphically what we're being shown is that the catalyst did not cause a shift. Okay, the lines remain horizontal, they don't change. Why does that happen? Remembering that the point of a catalyst is to speed up the rate of a reaction. Okay, and then also remembering in an equilibrium system we have two reactions happening, forward reaction and a reverse. The catalyst speeds up both of those reactions at the same rate at the same time. So therefore there's no shift in equilibrium. No shift in the equilibrium. Okay, so that's why the line stays horizontal. There you have it, fam. Stresses, shifts, spikes, bumps. Things are wild. Please make sure you're doing some practice questions to reinforce these concepts. And don't be shy to talk yourself through these ideas.